So we've learned about the Schmidt decomposition, which is a convenient form in which any pure bipartite state can be written that has the advantage of decomposing the degrees of freedom in the state between local degrees of freedom, which are given by the Schmidt basis, and global degrees of freedom, which are given by the Schmidt coefficients. So I keep referring to this decomposition as the Schmidt decomposition and the Schmidt coefficients, the Schmidt basis. This kind of prompts the question, is the decomposition unique? Is there something special about these vectors and coefficients? Could there be a completely different set of Schmidt coefficients and Schmidt vector that give me the same overall bipartite state? And the answer is yes, sometimes it can be the case. Sometimes the decomposition is unique, but sometimes it is not. You have to be a little bit careful about this. So this example is going to be about seeing when it's unique and when it's not. So just to remind you, what the decomposition says is that if you take any pure state psi AB, this state has a decomposition as sum over j of lambda j uj tensored vj, where the lambda j are non-negative coefficients called the Schmidt coefficients, and the uj and the vj are bases of the A and B systems respectively. So already here you can see that this decomposition is not going to be unique, because one thing I can do is that I can insert an arbitrary phase factor here, let's say ei theta j and e minus I theta j. So these two factors cancel out, so this is exactly the same vector as before, but now I can say, well, ei theta j uj, this is also a basis of system A, and e minus I theta j vj is also a basis of system B, and these are just as fine playing the role of a Schmidt basis. So at least we have this phase degree of freedom in the choice of the Schmidt bases. But there's more. So let's look at an example. This is our favorite example, the EPR pair. So let's have a 2-qubit state, psi AB, which is 1 by root 2 times 0 on A, 0 on B, plus 1 by root 2, 1 on A, 1 on B. Now, I've given it to you in its Schmidt form already. We have the two Schmidt coefficients, 1 by root 2 and 1 by root 2, and the Schmidt bases. For the A system, this is the standard basis, 0, 1, and for the B system, the Schmidt basis is again the standard basis, 0, 1. But now we know that we can write this particular state in many different ways. And if I write 1 by root 2 plus on A plus on B, plus 1 by root 2 minus on A minus on B, I have exactly the same state, but it looks completely different. Now I want to say that the Schmidt basis for the A system is the plus minus, the Hadamard basis. And for the B system, I'd want to say the same thing. So this is saying that these Schmidt vectors in general need not be unique. Here I have a completely different set of Schmidt vectors that gives me the same state. And the reason for that, as you can imagine, is that there's a degeneracy in the Schmidt coefficients. What's special about this state is that it has twice the same Schmidt coefficient, 1 by root 2. And in that case, the Schmidt vectors are not necessarily going to be unique. But it is the case that if the Schmidt coefficients are all different, then the Schmidt vectors are uniquely defined up to the phase degree of freedom that we saw earlier. And so that's something that's worth remembering and seeing why it's the case. Let me write down the statement for you. If the Schmidt coefficients are distinct, then the Schmidt vectors are unique up to phase. Note that this phase is important. So here, the fact that the lambda j's are asked to be non-negative means that this phase degree of freedom does not show up in the lambda itself, right? Because instead of pairing things up like I did over there, what I could have done is said, well, let's multiply lambda j by a phase ei theta j, and let's call this the new Schmidt coefficient. That's still the same vector, but I cannot do that because the Schmidt coefficient is supposed to be non-negative. So if you have a Schmidt coefficient that in general looks like a complex number, what you need to do is take the phase factor out and put it together with one of the Schmidt vectors. So these Schmidt coefficients are always going to be unique, and the reason is that you can recover them by looking at the reduced density matrices. Right? So this Schmidt decomposition lets you compute the reduced density matrices easily. So the reduced density on the system A, this will be the sum over j, lambda j squared, uj, uj. And similarly, the reduced density on B will be the sum over j of lambda j squared vj vj. So now we see that these lambda j, the modulus squared of the lambda j, are the singular values of the reduced density matrix. The singular values are uniquely specified, so the modulus squared of the Schmidt coefficients are uniquely specified. Since I am requiring these coefficients to be non-negative, then this number has a unique non-negative square root, and that gives me the Schmidt coefficients. So Schmidt coefficients are always going to be unique. The Schmidt vectors are given here by the associated singular vectors. So if the spectrum of the reduced density is non-degenerate, meaning that the Schmidt coefficients are all distinct, then the singular vectors associated to each of the coefficient is also uniquely defined. But if you have degeneracies, for instance, in the example that we had over there, the EPR pair, then the reduced density matrix is half identity. So the singular values are well defined. It's half and half. It has multiplicity 2. But the singular vectors, because of the degeneracy, then you have a degree of freedom. You could choose as two singular vectors, the 0 and 1 state, or you could choose the plus and minus state. And this explains the freedom that we had in the definition of the Schmidt vectors. Aside from that freedom, the decomposition is unique, and so it gives us a nice way to check when two bipartite states are the same. You simply compute the Schmidt decomposition for each of them, and you look if the vectors are the same or not. But you have to pay attention to this freedom that arises in the case where the Schmidt coefficients may not all be distinct.